got quite a surprise for you here today. We're going to start a brand new chapter, and that chapter is built upon this new idea of imaginary numbers. And as the new name kind of alludes to, it's kind of a wild topic, and we're going to see a lot of new things that we've never seen before in any of our earlier classes. So just to get us warmed up here, we want to get this definition in our notebook. It says, when a real number is squared, ask yourself, what happens every time you square a real number? And basically a real number is any number that you've currently worked with up to this point. It could be a whole number, it could be decimals, it could be positive, it could be negative, any of those such. The answer is guaranteed to be what? And I'm going to use a new phrase here called non-negative. What does non-negative mean? Well, non-negative means, aka it's either positive or it's zero, but it's definitely not what? It's definitely not negative, okay? So, and I think that makes sense. We've done this a lot. Let's just pick a negative number. If you square it, by definition, you're multiplying that number by itself. And so if you started with a negative and you multiply by another negative, you're now guaranteed to be a positive 16. There's no way that you could possibly square a number and end up with a negative answer. It's just physically, mathematically impossible. Therefore, the square root of a negative number is impossible under the real number system. It's just physically impossible. So, this fact has great ramifications when we're finding the roots or the x-intercepts of a parabola. So let's go take a look at an example and see how we're going to handle it. So here we go. We're going to start with the good old function y equals x squared, probably one of our friendliest graphs and friendliest functions we work with. And now I want you to consider a very similar parabola, f of x equals x squared plus 1. So the first thing is, how is the original x squared graph shifted in order to produce f of x equaling x squared plus 1? And I'm going to say that it is a shift upward of 1 unit. All right. So basically what's going to happen is the vertex, which is a 0, 0, is now going to be here at 0, 1. Every other point went up 1 unit all the way across the board. And we now have a new parabola that looks similar to this. All right. So what can be said about the x-intercepts? Well, there are none. There is never a moment where that parabola crosses the x-axis. It is entirely above. So now the last thing we're going to do is we're going to prove that algebraically that these roots do not exist within the real number system. Anytime you want to find the x-intercepts, we simply set the function equal to 0. What I'm going to do is I'm going to go ahead and I'm going to subtract the 1 over. And then what I'm going to do is I'm going to take the square root of both sides. So we get something like this, x equals plus or minus the square root of negative 1. And we're going to say that is impossible. We cannot take the square root of a negative number within the real number system. So as mathematicians, we certainly have created quite the problem. We agree with the fact that graph has no x-intercepts, and we've proven it both graphically and algebraically, but we'd still like to have an answer to that problem. We'd still like to have some kind of an answer when we're all said and done. And so here's what we're going to say. Since we cannot solve this equation using real numbers, all right, we introduce a new number, and I wish I had some sound effects here for a little drum roll. And that new number is called an I. So it's a lowercase I. And I is the basis of imaginary numbers. Now the key though is, even though we think of I as a letter, it's very important that from this point forward, starting right now, starting today, that we now start to think of I as a number, okay? Its definition allows us now to have a result when finding the square root of an imaginary of a negative number. And its definition is given here below. So this is the one thing that you want to walk away with today is, by definition, I is a number, and I is equal to the square root of negative 1. Just keep telling yourself over and over again, I is equal to the square root of negative 1. I is a number. Alright, just a little practice here, simplifying some square roots of negative numbers. And so what I'm going to do is I'm going to break these down very strategically. I'm going to rewrite radical 9 as the square root of 9 times the square root of negative 1. And the square root of 9 is a 3. And by definition, this is our new definition tonight, the square root of negative 1 is an I. So the square root of negative 9 is 3i. Let's do 100 times negative 1. So that would give me 10 times I. So bottom line here is, as soon as you see a negative number here, you know you're going to have a what in your answer. You're going to have an I in your answer. You see a negative, you've got an I in your answer. Those two ideas go hand in hand every single time. All right, let's try a couple more. These ones are a little more challenging. 32 is not a perfect square, so what I'm going to do is I'm going to do 16, and then I'm going to do my negative 1 times 2. You know, normally if the negative wasn't there, we'd have just done 16 times 2. So today I'm going to say it's 4 times I times radical 2. There's my answer. I had a negative, therefore I have an I in my answer. Last one, I'm going to say radical 9 times radical negative 1 times radical 2, and it gives me 3I radical 2. All right, little review. We're going to incorporate a concept that we did last week with this new idea today. We're talking about incomplete quadratics. And by definition, an incomplete quadratic is one who is missing what? They're missing their b term. All right, so we're missing the b term. And so what we're going to do is on this first one, I'm going to subtract 8 from both sides. All right, now just in case it's too fuzzy, the original equation said 5x squared plus 8 equals negative 12, and I'm going to subtract 8 from both sides. So I've got 5x squared equals negative 20. If I take this, I'm going to divide both sides by 5 because I'm trying to isolate the x squared. And that's going to give me x squared equals negative 4. And then if I do take the square root of both sides now, I'm going to get x equals plus or minus 2i. Again, by definition, as soon as you see that negative, you're going to have an I in your answer. So plus or minus 2i is my answer to that quadratic. All right, let's try b. The equation says 1/2 times x squared plus 20 equals 2. So first move, I'm going to subtract 20. And that's going to leave me with 1/2 x squared equals negative 18. The next thing I'm going to do, and you can say this one of two ways. We're either going to divide both sides by 1/2, or what I like to say is I'm going to multiply both sides by 2. Whatever we do to one side, we're going to do to the other. And that's going to give me x squared equals negative 36. And last but not least, I'll take the square root of both sides, and that's going to give me plus or minus. Don't forget that plus or minus. As soon as you're solving an equation, and that's what's different compared to the last slide, we weren't solving equations, we were just simply simplifying radicals. And whoops, got my 6 in there and my I. All right, we're getting there. Let's try one more with a complete or incomplete quadratic. The equation says 2x squared minus 10 equals negative 36. I'm going to go ahead. What's your first move? Yeah, let's go ahead and add our 10 over to the other side. This is a great one. Great time to hit that pause button. Try to solve this one all on your own. I got 2x squared equals negative 26. I'm going to divide both sides by 2. And that's going to give me x squared equals negative 13. And then if I do take the square root of both sides, I get a very ugly, let's see. Now I'm breaking that into radical 13, which cannot be simplified, and radical negative 1. Now the radical negative 1 does produce an I. Almost forgot my plus or minus. Radical 13. And that is the simplest form of radical negative 13. Okay. I wanted to bring up a great example of a multiple choice question that could show up on our next test. I think we're ready to try this one, and I want you to go ahead and try it all on your own and then see if you come on back and see if you agree. All right, so I said the product, think of it like, ask yourself, what would I do if it was 5x times 6x? That'll help. We would all agree that that's 30x squared, right? So now we've got 5i times 6i, so I'm thinking, all right, 30, and then I squared. I times I is I squared. Now this brings up a whole new ball of wax. What in the world is I squared? Well, let's go back to our definition. We said that I was equal to the square root of negative 1. So what happens if I want to square both sides? Whatever we do to one side, again, we do to the other. I would end up with I squared equaling, again, the square kills the square root, and we get negative 1. So we've just proven, and this is very useful, that I squared is equivalent to negative 1. So I'm going to substitute my negative 1 in for I squared, and I end up with negative 30, otherwise known as choice 3 for this answer. Well, I absolutely love things that have patterns and are kind of cyclic in nature, or they move in patterns and cycles, I should say. So here's what we got cooking here. We're going to say that the powers of I display a remarkable pattern. Okay, That's the big key. The powers of I display a remarkable pattern that allows us to simplify large powers of I. Like what's I to the 99th power? What's I to the 200th power? Into one of four cases. Okay, there's only four possible outcomes we could have, whether it's I to the 90th or I to the 200th or I to the billionth power. So let's do a couple of examples and let's see if we can discover the secret pattern together. Alright, so by definition, anything raised to the first power is indeed itself. So we're just going to say in our notebooks that I to the first power equals I. And we want to stay very organized and crisp as we put this in our notebook. We just proved on the last slide that I squared is equal to -1 because we squared both sides. Alright, now mathematically, how are we going to do I cubed? Well, remember that x times x squared is equal to x cubed. Agree? So therefore, I times I squared is equal to I cubed. So what I'm going to do is I'm going to take the I and the I squared and multiply them together and get -I. Now we do I to the fourth, and hopefully you say, yeah, x squared times x squared is x to the fourth. Therefore, I squared times I squared is equal to I to the fourth. So if I take my I squared times itself, I'm going to get +1. Alright, so I'm going to continue to do a similar pattern here. I'm going to switch colors just a little bit. I to the fifth is really I squared times I cubed, because when you're multiplying like bases, we just add those exponents, and that's something we've talked a lot about. So I'm going to take my I squared, I'm going to multiply it by my I cubed, and that's going to give me +I. Let's see, I to the sixth is I cubed times I cubed. So let's see, this guy times itself would be +I squared. And what in the world is +I squared? Yeah, that's -1. Okay, I to the seventh. Let's think of that as I cubed times I to the fourth. So I'm going to multiply this guy by this guy and get -I. And then the last one, I to the eighth. Well, I'm going to think of that as I to the fourth times I to the fourth, so it's this guy times itself, which gives us 1. Now, if you kind of step back and we strategically organize these, you can see the result. All right, our answers were from left to right, I, -1, -I, +1. Okay, the next row goes the same way, I, -1, -I, +1. And if we continue to use the same pattern, it would repeat itself over and over and over again. So what I'm trying to say is I to the ninth, because of this pattern and the repetition we see, we know it's going to be I. I to the 10th power is going to be -1. I to the 11th power is going to be -I. I to the 12th power is going to be +1. And the pattern continues to repeat over and over and over again. So there's really only 4 possible answers that we could get. Alright, we see from this pattern, you're either going to get a -1, a 1, an I, or a -I, and the pattern will continue to repeat over and over again. So let's summarize that on the next slide. Okay, so we have what's called the power of I wheel. And this wheel is really cool when it helps you remember the 4 original outcomes, and and we can build off of that. So here's how the wheel goes. It starts off, I always start with I to the 0, and then I to the first, and then I squared, and then I cubed. And if we can memorize these 4 outcomes, you're going to be in great shape. And just like in all of math, anything raised to the 0 power is indeed 1. Anything raised to the first power is itself. We showed that I squared is -1, and we showed that I cubed is -I. So it goes around in those cycles. In other words, let's see, I to the 0, I to the first, I squared, I cubed, I to the fourth would be 1, I to the fifth, I to the sixth, I to the seventh, I to the eighth, I to the ninth, I to the 10th, I to the 11th, I to the 12th, so on and so on and so forth. So ultimately, the question becomes, how am I going to use this pattern to help get to the answer as quick as possible? In other words, how are we going to cheat a little bit? What we're going to do is we are going to focus on the remainder, okay? And it's been probably years since you talked about this idea of a remainder, all right? But because the powers repeat every fourth power, the first thing we're going to do is we are going to divide the given exponent by 4, okay? When we do so, the remainder becomes the new exponent. The remainder becomes the new exponent. And then the last step is to just simply evaluate the new problem with the new exponent. All right, so I'm sure that sounds like a little bit of gibberish, but we're going to do tons of examples. Now, the other thing is I do want to do a little crash course on dividing by 4 and remainders, okay? Let's see. For instance, 5 divided by 4, well, 4 goes into 5 once, but more importantly, the remainder is 1. 6 divided by 4 has a remainder of 2. 7 divided by 4 has a remainder of 3. And 8 divided by 4, well, 4 goes in there perfectly, so the remainder is 0. So hopefully that brings back some memories of remainders. But we're going to use our calculator to help us a little bit tonight. And so when we divide by 4 on the calculator, you're going to get one of 4 options. If you don't get a decimal at the end of your answer, in other words, it's 0.0, that means, again, the remainder is 0. If you get a 0.25 on your calculator, that means the remainder is 1. If you get a 0.5, the remainder is 2. And if you get a 0.75, that implies that the remainder is 3. So we're going to do a lot of calculator work just to make our life a little simpler and quicker tonight. And we're going to rely on those powers, and we're going to go back and we're going to use that wheel as well. So let's go try some. So here's where we really need to focus so that we can hopefully walk into class tomorrow and do the best we can on the worksheet. But the first thing I want you to do is I want you to take the exponent they gave you, because we're trying to evaluate I to the 38th power. Now you could grab the wheel and go around the wheel 38 times, but again we're thinking there's got to be a quicker way. If I do 38 divided by 4 on my calculator, the calculator says it's going to be 9.5. I don't care about the 9. Throw the 9 away. All we're focusing is on the 0.5. What that means, that implies that there's a remainder of 2. Okay, so I to the 38th is really I squared. I'm replacing the old exponent with the remainder. And I squared, as we know, is -1. And ladies and gentlemen, that is your answer. Let's try another one. Part B, 21 divided by 4. The calculator says it's going to be 5.25. What do I want you to do? I want you to throw away the 5. We don't need them. The 0.25 implies that the remainder is a 1. So let's say I to the 21st power is equivalent to I to the first power, which is equivalent to just good old I. So there's your answer. All right, we'll scroll here a little bit. 83. Okay, let's grab 83. Divide him by 4. Calculator says 20.75. And I told that calculator, throw the 20 away. All I need is a 0.75, and that means that the remainder is a 3. All right, so I to the 83rd is equivalent to I to the 3rd, and that is -I according to the wheel. So -I is my final answer. And then one more here. Let's see, 40 divided by 0. The calculator said the answer was 10. What does that mean? It means, well, there is no decimal, so the remainder is what? The remainder is 0. So I to the 40th is I to the 0, and just like any other number in math, when you raise it to the 0 power, you get a 1. All right, we need just a little bit more practice here, so I want to throw out another problem here. Let's try I to the 121st power. Again, we don't want to go around the wheel 121 times if we don't have to. So I'm going to grab the exponent they gave me. I'm going to divide it by 4, and the calculator says that 4 goes in there 30 times and 0.25. So again, throw away the 20. The 0.25 is what you want. 0.25 implies that the remainder is a 1. I to the 121st power is equivalent to I to the first, which is an I. All right, let's try another one. Here's a great one. Let's go ahead and hit the pause button on this one. Let's do 223rd power. Go ahead, hit pause. Try this one on your own. See if we get the same thing. So on my calculator, I did 223 divided by 4, and the calculator said that that's going to be 55.75. Throw away the 55. What does the 0.75 mean to you? That means that the remainder is 3 units. Okay, so I to the 223rd is really I to the 3rd, and according to the wheel, I to the 3rd is -I. So there's my final answer. All right, we're going to finish tonight with a heck of a bear here. Again, another question that could show up on our next test. And they want to know which one's equivalent to 5x to the 16th plus 3i to the 23rd plus I to the 26th. You see those plus signs? We can't add terms. We're not allowed to add terms unless they are like terms. And these are not like terms because they all possess a different exponent. Because the exponents are different, they are not like terms, and I am not allowed to add them. So what am I going to do? Here's what I want you to put in your notebook. We are going to simplify each individual term. Simplify each individual term. That is my game plan. That's the plan that I'm going to follow here. So let's focus on that first term. If I've got my 5, but what is I to the 16th? So I divided 16 by 4. And the calculator said it goes in there 4 times with no decimals, so I have a remainder of 0. So I'm just going to write I to the 0 for now. And then I've got plus 3. When I did 23 divided by 3, the calculator said 5.75. I threw the 5 away. I had a remainder of 3. And then I finished with, let's see, they threw me I to the 26. 26 divided by 4, let's see, what was that? That turned out to be 6.5 on the calculator. Throw away the 6. The 0.5 means a remainder of 2. So now I just clean these up. I to the 0 is really 1. 1 times, well, let me go nice and slow. I'm just going to substitute the 1. Let's see, I to the 3rd is really negative I, and I squared is negative 1. So let's go ahead and clean them up just a little bit more. Let's see, that's a 5 minus 3I plus a negative 1. Combine the 5 with the negative 1 and get a 4 minus 3I. And if you look back up at the choices, it matches choice 2 beautifully. But the key here is, and that's what I want you to walk away here, is knowing we had to simplify each term first. There were no like terms when we started, but once we simplified them, we did find that there were some like terms that we could combine and make it a little more simpler. So good luck, and we'll see you tomorrow.